Okay, for this one, it is the experiment is repeated, but now by using different intensity of lights, of the incident lights. Okay, it is observed that, okay, for low intensity and high intensity, the difference is in terms of I maximum or I saturated. Okay, in terms of pattern, the behavior of it almost the same. Okay, initially, okay, it's almost straight line. If you make it bigger, this one is almost straight line initially. Okay, linear, almost linear here, right? But then as the voltage applied on the power supply, the delta Vs, okay, is increased, okay, it reached one single value. We call it saturated current. For current produced by the ejection of the due to the ejection of the electron, it reached a single amount, or we call it I saturated. Here I saturated. So goes the same. Here we have I saturated. Right? Okay, so saturated value means that maximum value can be reached. No more ejection of electron after that. That is the maximum number of photoelectron can be ejected. Okay, when you use, let's say, the blue color lights, okay, or the blue color incident lights, okay, or photon, okay, producing this pattern, okay, where it's representing low intensity. For a high intensity of incident lights, this is the pattern of the current versus applied voltage graph. Okay, but doesn't matter whether it's low intensity or high intensity, both of them, okay, going to reach one single point, which is equivalent to negative delta Vs. Okay, the delta Vs is actually stopping potential. Why is it named as stopping potential? Because this is the voltage needed to stop the most energetic photoelectron, to collect the photoelectron or electron being ejected from the metal surface. At voltage equals to or more negative than the negative delta Vs, the current will be zero. What does that mean? What does that mean by current being zero? It means that, okay, no ejection of electron. Photoelectron. Okay, if you refer to this graph, the current detected is directly proportional to the intensity of the incident light. Right, let's proceed. Einstein explanation about the phenomenon of photoelectric effect. Okay, Einstein explained that a tiny packet of light energy called photon would be emitted when a quantized oscillator, okay, jump from one energy level to the next lower one. Extended Planck's idea of quantization to electromagnetic radiation. So the photon's energy would be E equivalent to HF. Each photon can give all its energy to an electron in the metal. So this is the reaction of 1 to 1. Okay, one photon give out its all energy to one electron. Okay, the maximum kinetic energy of the liberated photoelectron is Ke max equivalent to HF minus work function. So this is actually Ke max equivalent to HF minus work function. And it is known that Ke max equivalent to E delta Vs. Right? Okay, so this one. So this is actually explaining the same thing of the output that we discussed just now. Talking about there is electron ejected when the incident lights having frequency bigger than or at least equals to the cut-off frequency, minimum required frequency. Okay, classical physics or wave theory of physics cannot explain Why is this happening? Cannot explain. Because they thought that it doesn't related to frequency. They thought that the number of electron being ejected will be depending on the intensity, the brightness of the incident lights only. So it doesn't matter what frequency you use. Supposedly there must be ejection of electron, whenever the incident light having a high enough intensity. But it is explained well by quantum or particle theory, because from particle or quantum theory, it is known that frequency is the main character that going to influence, because the energy is directly proportional to the F, where based on formula E equivalent to HF, right? Then second part of facts, that going to be explained. The second is about kinetic energy maximum of the electron, of the ejected electron or photoelectron, is directly proportional to the frequency. Based on classical or wave theory, they cannot explain this because they thought nothing to do with the frequency. However, for quantum or particle, for sure it is explainable, because of, again, this equation, E equivalent to HF. And the E, if you refer back, this one, KE equivalent to KE max equivalent to HF minus work function. Right. Next one, is about, there is ejection of photoelectron, instantaneously, where the time taken is less than 10 to the power of negative 9 seconds. So classical wave or wave theory, also again cannot explain about this one, because they thought that if you leave it there for 10 hours and the electron going to gain enough energy, somehow the electron must be able to release itself from the bonding energy of the atom. But that is not the case. That is not happening. If it is at the right frequency, based on quantum or particle theory, there will be ejection of electron, because based on the concept of one-to-one reaction. What does that mean? One photon going to give its all energy to one single electron. So it does not wait for a long period or time. It can continuously eject the electron from the bonding of atom. Right. The next one will be about the current produced. The current produced or observed in the photoelectric effect circuit, directly proportional to the intensity of the incident lights. So based on classical or wave theory, yes, it is agreed, it is expected like this, because the intensity representing the energy of the incident photon or lights. So goes the same to the quantum or particle theory, where it says that the current produced, the energy is depending on the frequency, and the frequency also directly proportional to the intensity of the incident light. So this is a summary of the photoelectric effect phenomenon. Okay, when quantum or particle theory of physics for lights, can explain every single facts that happening within the photoelectric effect experiment. For classical of wave theory, it only can explain one information. The rest of the information it failed to explain. That is why it is needed to have quantum or particle theory. Okay, so what does that mean by particle theory? It means that light is treated as particle, not only wave. Okay, in classical, light is treated only as wave. Okay, so what does that mean by particle? Again, the energy is discrete amount. Okay, in quantization of energy, or the energy being quantized, we call it. Alright. So photocell is the application. Okay, is the application of the photoelectric effect. Okay, this is an example of the photocell. We use it a lot in for example, elevators, garage door openers, street lights. Okay, when lights of sufficiently high frequency falls on the cell, a current is produced. Then the current going to be used up to give information that you need to open the door, you need to shut down the door. So that is the way is where we apply photoelectric effect phenomenon, or findings. So let's try out question number 10, page 883. So in this question, lithium, beryllium and mercury have work function of 2.3 EV, 3.9 EV and 4.5 EV respectively. Light with a wavelength of 400 nanometer is incident on each of these metals. Which of these metals emit photoelectrons in response to the light? Why? Alright, so we need to know the energy of the photon incident on the metals firstly. And then we need to compare whether the incident energy of the photon at least equals to the work function, because the work function is minimum required energy to eject a photoelectron. Right. So to answer part A, E of a photon equivalent to HF, which equivalent to HC over lambda. Right. Why is it C? It's supposed V over lambda, right? But then I'm using C because we're talking about light. So the speed of light is C. 3.0 times 10 to the power of 8 meter per second. So Planck constant 6.63 times 10 to the power of negative 34 times the C, 3 times 10 power of 8 divided by 400 nanometer. Don't forget to convert the prefixes. Negative 9. Okay, but if you see here, your unit going to be in joule. If you are using this formula, your final unit will be in joule, right? But then our given work function is in EV. Therefore, we need to convert. So times with, what is the conversion factor? 1 EV, this one in joule, 1 EV per 1.6 times 10 to the power of negative 19 joule. So finally, we will get the answer is 3.11 EV, electron volt. So if we compare this value, okay, to this value and this value and this value, for sure only lithium will exhibit the photoelectric effect. Why is it? Because the E of the work function of the lithium 2.3 eV electron volt, whereby the incident light or photon energy is 3.11 eV. If it is incident on 3.9 eV of work function, the metal with this work function, it cannot eject any electron as well as this one, because the value of this is smaller. So only lithium going to experience photoelectric effect, where electron going to be ejected whenever photon with this amount of energy is incident upon it. Therefore, okay, only lithium exhibit photoelectric effect. Okay, that is for part A. For part B, right, find the maximum kinetic energy, the photoelectrons in each case, since we only have lithium with a possible photoelectric effect phenomenon. Okay, so for part B, kinetic energy maximum of the photoelectron is equivalent to energy of the photon minus work function. Work function is minimum required energy to eject an electron from a metal surface. So the E of our photon just now 3.11 eV minus the work function of lithium is 2.30. End up, we're going to have 0.81 eV. Right. So this is the answer for part B. You may convert this into joules by multiplying by this factor all over again. Okay, rearrange. Alright, next one. Okay, question number 12. Right, page 883 as well. Okay, so the question asking for two light sources, okay, are used in a photoelectric experiment to determine the work function for a particular metal surface. When green light from a mercury lamp with lambda of this is used, a stopping potential of 0.376 volt reduces the photocurrent to 0. Okay, based on this measurement, what is the work function for this metal? B, what stopping potential would be observed when using the yellow light from a helium discharge tube where the lambda is 587.5 nanometer. Right, so let's try to solve for part A. Right, the maximum kinetic energy of the ejected electron or photoelectron, okay, Ke max is equivalent to E delta Vs. Right, those the stopping potential is given to us 0.37, stopping potential 0.376 volts. Okay, when the incident light has a wavelength of 546.1 nanometer. So the equation from photoelectric effect will give us information about work function. So the work function of this metal can be figured out by using this formula. E photon minus Ke max. The E of the photon itself is Hc over lambda minus E delta Vs. Right? So equivalent to 6.63 times 10 to the power of negative 34, okay, times with 3 power of 8 over the lambda 546.1 times 10 to the power of negative 9, right? Do not forget to convert 1 EV over 1.6 times 10 to the power of negative 19, okay, joules, right? And then minus the work function, 0.376 EV. So you will get your answer 1.9 electron volt. Right, this is part A, and here will be part B. Okay, for part B, what stopping potential would be observed when using the yellow light from a helium discharge where the lambda is 587.5 nanometer. Okay. If the light of lambda with 587.5 nanometer is incident on this metal, the maximum kinetic energy of the ejected electron, okay, E delta Vs, okay, which is the Ke max, which is equivalent to Hc over lambda minus work function, okay, is equivalent to, okay, 6.63 10 to the power of negative 34 times 3 10 to the power of 8 divided by 587.5 10 to the power of negative 9. Okay, conversion 1 over 1.6 10 to the power of negative 19 minus, okay, 1.9 EV just now. Okay, right, so you will get your answer is in terms of 0.216 EV. Okay, so from here, okay, from here, this is your Ke max, right? Ke max. Ke max. Right, so E delta Vs is equivalent to Ke max, 0.216. So if you want to know the delta Vs, equivalent to 0.216 divided by the E. Okay, this is in terms of EV. Right, so finally you will get your delta Vs is equivalent to 0.216 volts.